come on, come off, the whole line, until it's deprotonated. Deprotonation is equilibria, passage between two similar species. This guy really sits more to the right than it does the left, but we never said we're going to ding you on that, right? We said equilibrium, right, left. Those are your three choices. So this is equilibrium. This is resonance, equilibrium, attack, come on and off, deprotonation. This really sits more to the right than it does the left. Because again, we're protonating in nitrogen, not in oxygen. Leaving group argument, acid-base chemistry. Okay? Yes? So this guy really, it sits, as we talked about last time, right? As we draw up this final product, this begins to have less reversibility associated with it. But equilibria is fine here. Okay? There are questions about this? Okay. All right. Let's talk about a couple of the homework questions. You all turn this in and see where we go with that. All right. I see a lot of you didn't try that acid-base section. I really think that would have been a good one to try because you guys are avoiding something that you can't avoid on your next test. So how about we sit and do the acid-base section for a while? That'll be good for all of us. For sure I thought, oh, they're all going to try this. This isn't bad. And then you probably are all like, what the heck? Yeah. I'm going to do them all. Yeah. I'll get to J. Get there. So the first one is propanol and sodium hydroxide. This hydrogen that I've just underlined as propanol. Yeah.
Are we going towards aldehyde condensation with this? Because that's that's where I got confused. Okay.
So this is just acid-base chemistry, right? Just the acid-base reactions that begin. No crazy, moving forward to things that can happen. Okay, so this guy, the hydrogen that I've underlined, is the hydrogen to lead. There's two types of hydrogens, one off of an sp2 carbon, one off, well actually I guess three. One off of the alpha carbon to the carbonyl, and one off the beta carbon to the carbonyl. The alpha one's got the highest pKa, meaning it's the most acidic. Its pKa is between 16 and 20. So this is pulling out the new pKa sheet. These are ones that we need to begin to know. So when I react this with hydroxide, I'm going to get the deprotonated propanol at the alpha site, and then water. Water's doing the pulling, right? If this is my base, it's going to pick up that proton to become my conjugate acid, right? This is the base. It's going to pick up that proton to become the conjugate acid, and I'm going to be left with a conjugate base at this site, right? So this guy's 16, this guy's 16 to 20. This should be an equilibrium arrow. Yeah?
So you knew that hydrogen was that pKa because of where it fits in the molecule.
That's exactly right. So what is so special about that hydrogen, right? And it is the acid-base chemistry. Okay, so if you look at all of those family members, this is actually a good question. And I'm going to ask even a further question. If you look at that alpha proton from all of these, I question you, what do we think about the pKa of all of these? This is something I'm asking you. Right? And then you have your ketones and aldehydes, of which that's an example, right? Okay? So there's a few that you have on your sheet. We say this is between 16 and 20. This one's on your sheet. This is 20 to 25, generally what they are. This doesn't pull this one, surprisingly. You would think that it does, but it's not after that one. Okay? It's actually after this one out here. So I'm going to make this something like that. This guy here is roughly about 25 too, the hydrogen of the amide. Very surprising. The question is, where do these sit in relation to these others? So really it is, what makes this, let's focus on the alpha protons, what makes these protons so acidic? Resonance. Resonance is what makes stable than this conjugate base. Because that's what the numbers mean to me, right? 20 to 25 says I'm less acidic. And if I'm less acidic, my conjugate base is less stable. There's a reciprocity between acid-base strength. Reciprocity between acid-base strength. So what is it about this conjugate base that's less stable than this one? Yeah.
The pi electrons on the OR group don't resonate.
Okay, so the OR groups, that's not that they don't resonate, but it is to do with the OR group, yeah? They push electrons as well, right? Wouldn't this conjugate base here be competing with the ability for these electron pairs to donate to form a resonant structure? There's competition there between those, right? So hence, you have a less stable conjugate base because this may, right, push electron density toward the carbonyl, hindering that electron pair with a negative charge to resonate. There is not that competition here, right? This electron pair is only moving in one direction, no hindrance, nothing that is halting its movement. Its conjugate base is more stable, okay? Now, what's interesting about the acyl chloride and the anhydride is their reactivity of the carbonyl center begins to impede the acid-base chemistry as much, but the question still rides, what do we think potential pKa's could be there? This class never wants to own up, so how about we start with a clicker question on that next class? You'll all own up there. That's how I get you to own up. So we're going to own up. The question is, what is it about how these relate to what I've told you and what we know about here? Based on knowledge we're talking about, right? Based on things we're talking about here. Yeah?
With the anhydride, end up being more stable than the OR group, just because it would pull electrons away and it would give it less competition to have a low charge.
Okay, so you are coming up with a great argument, and the argument centers around the reactivity order that we've already talked about with this chart, right? We've already talked about the resonance capabilities of the functionalities in this chart, which is exactly what you're going toward. I ask you to continue that. Yeah? You had your hand raised? Yeah. Sorry. Go ahead.
The anhydride, the oxygen is also next to the electron pairing of the carbon, so where the electron pairs on oxygen go.
Okay, great. So we also note, which is exactly what we were talking about before, that you don't resonate only in this direction, you resonate in the ulterior direction. Is that the right word? Anyway, the other direction as well, and hence, you don't have to worry about it as much. Did you want to say something? Okay. All right, so your guys are riding in the right direction, so continue to think and you're able to go Google it as much as you want. See what you can figure out by Wednesday's class. We're going to start with that. So these alpha sites can become deprotonated readily, okay? Especially these esters, aldehydes, etc. Okay. So let's see, what else do we have? Potassium methoxide and butanoic acid. Everybody should have gotten that as an acid-base chemistry between the carboxylic acid and the methoxide. So this should have sat to the right. Yeah.
Should we even consider the amide? Amide?
No. So this guy will sit to the right, 5 for the pK over here, 16 for the one on the right. This sits to the right. Everyone understand that one? Okay. All right, isopropanol with acetic acid. This requires that I know which one's the acid, which one's the base. This pK is 16, this is 5, therefore this is the acid, this becomes the base, right? So I should get the protonated alcohol, this is the conjugate acid, and the carboxylate. potassium hydroxide with methyl propanoate. Methyl propanoate is this guy.
That's
And we have,
Dr. Dixon.
yeah.
That's -2.5, right?
Negative, yeah.
Yeah, there's a point in there. It's not 25. There's nothing that goes lower than -10. There's a dot there. Okay. And methoxide, right? Potassium hydroxide. Yeah, okay. Here we go. What do we think is going to happen here?
Gonna attack the.
What?
Alpha carbon.
Gonna attack.
Okay, alpha carbon. I agree. That's the acid-base reaction. What does the acid-base reaction compete with here? It competes with nucleophilic attack. Okay, great. So this guy over here is about 20 to 25. On the right side, we have water, which is 16. So in essence, this sits to the right, to the left, pardon, more than it sits to the right, correct? It would really depend. Are we more toward 20? Or are we more toward 25? Am I right? So that's going to change what we're going to see. So this is a place where we compete. We compete with attack at the electrophilic center. So there is correspondingly the ability for that OH minus to come in right to this center, right? And start doing a hydrolysis reaction. Does everyone see that? What's going to win out? Do we know? No, we don't know. And we shouldn't know. But here's a question for you. If I wanted to deprotonate that alpha center, that specific one right there, there's other bases I can use. I don't have to use that one, right? OH minus is causing me trouble, right? Deprotonate that center, all right? It can attack the carbonyl center. Okay, now I'm in trouble, right? Here are some other bases I can use. I can use O minus CH3. I can use O minus CH2 CH3. Or I can use NH2 minus. One of these is the best one to go with. A, B, or C. All want to go for that nitrogen, right? Yeah, no.
B.
The acid-base chemistry might be certainly better in that case, but all right, let's start with C and prove why not C. How about that? So I get an NH2 minus in here. This looks good, right? Acid-base chemistry looks good. The question is that nitrogen going to attack that carbonyl center? Yeah.
Just go back to like how you said nitrogen is more basic than oxygen.
Nitrogen's definitely more basic than oxygen. I'm not doubting that. Absolutely. So I am agreeing that this acid-base chemistry is a go, right? I have on the left the alpha protons pKa 20 to 25, and on the right I have NH3 36. That sits to the right, that acid-base chemistry. But now I'm saying to you, can it attack the carbonyl center? And the answer to it is yes, right? Why can't it attack at the carbonyl center? There's no reason it couldn't attack the carbonyl center, right? So if it attacks the carbonyl center, what am I going to get? I'm going to get an amide, right? I'm going to get an amide, yeah.
Why is the terpene not
What TV? Oh, we're getting there. Hold on just a second. So this is a problem, right? What if any of this happens? I'm going to get some amide in the flask. Do we like that? No, we don't don't like that. Actually, if we want to use a nitrogen nucleophile, we usually use lithium diisopropylamine. That's a good nitrogen nucleophile. Someone tell me, does everyone know what lithium diisopropylamine looks like? Try and reason it out. Diisopropylamine. What do you think that looks like? Diisopropylamine,
Antlers.
right?
Looks like
An action, right? Is
looks
everyone
like
with me?
DSP.
Lithium diisopropylamine? Yeah? Okay, why would this be good? It's bulky. There you go. Lithium diisopropylamine is bulky. It's not going to do the carbonyl attack that NH2- will, right? So lithium diisopropylamine is a better choice if you want to do that. But actually, we wouldn't even want to mess around with trying to get any amide in there. So really, we're going to consider these guys not so good. Now we're left with A and B. For some reason, you guys want B. What's B? What's so great about B? Oh, it's bigger. That's a good one. Yeah, no, A is the right answer. I know. Here's why. Yeah.
Because if A does do the nucleophilic attack, you get the same thing as you had in the
Beautiful. I could just kiss you. I won't. You're safe. You're going to be sitting back. He's like, oh, no. Okay. Absolutely right. Absolutely right. If you use methoxide, it matches my ester linkage. It's a direct match. So if it's going to do any swapping out, right, it's going to be the same thing in the end. Does everyone see what I mean? Anytime you want to deprotonate the ester and not mess around with side reactions, because we're really getting to a point in the material where lots of things could happen, if you really only want to focus on deprotonation, you match the base to your OR group. It's exactly what you do. Is everyone with me on that? So, the hydrolysis reaction was a potential problem with the acid-base reaction in E on the homework. Okay? Yes? All right. These last few ones are actually really good. Someone tell me where this one comes from. This is, now we're on F. Rubidium chloride and the conjugate acid of ethylamine. Rubidium chloride, skipping the rubidium because I don't care about it, and the conjugate acid of ethylamine. Okay? Where would this come from?
DNA.
Thank you.
Not DNA.
Thank you.
Amino acids.
Someone tell me where and when I would get down to looking at the acid-base chemistry between rubidium chloride or chloride, Cl-, and the conjugate acid of ethylamine. Go.
Amino acids.
Conversion of an acyl chloride to
Obviously not.
an amide. Right? To an amide. This is where this acid-base chemistry comes in. What does this acid-base chemistry tell me? If it's going to rescue my nucleophile. If I'm going to be able to rescue my nucleophile. Okay, great. So, I have Cl-, clearly that has to be the base. It has a negative charge, right? Most often, that's the base. This is positive, hence most often the acid. So I'm going to get HCl out of that, and ethylamine. -7 for HCl, 9-ish for my protonated ethylamine. This reaction sits to the left, right? This is what we see in the analysis when we're talking about the conversion of an acyl chloride to an amide. So what does this tell me? How much amine do I need to add? 2 moles. 1 mole is used to do the actual reaction. The second mole is used
Acid base.
As a base. The second mole is used as a base. Can anyone think of, instead of, let's say ethylamine is really expensive. It isn't, but let's just suppose. It's very expensive. Can anyone think of something that I'd be able to add to this reaction pot that would, I wouldn't need to add 2 moles of my really expensive amine? What can I add that's going to sop up for me, never act as a nucleophile, never going to get involved as a nucleophile? Nope. Cubitalxide can get involved as a nucleophile. It's bulky. It's not so good. I agree with that. Yeah? Pyridine. There it is. You guys know that song? Whoop! There it is. Yeah, that's what we do in our house. I have my kids doing that now. They go, whoop! There it is. Even my son. That's a good one. All right. Pyridine. Pyridine is a great base, not a nucleophile. We all know why it's not a nucleophile, right? It's aromatic. That's good. That means, it's good. Even its conjugate acid is aromatic. But why isn't it a nucleophile? Because it acts like a tertiary amine. You go. That's right. It doesn't have a hydrogen on it, right? To deprotonate. One of the requirements of a nitrogen as a base is that it has a hydrogen on it to pull after its initial attack. It behaves like a tertiary amine. Good job. Good learning from previous exams. Okay. This was an exam question previously. All right, great. So this is no good. This would be the same thing. If you look at the next one, it says sodium phenoxide with a conjugate base of butylamine. Now this is a very special case. Sodium phenoxide, so phenoxide is this guy, with the conjugate acid of butylamine. What do we think this is? This is what? Found in what reaction? What conversion? I'm going to give you the general scaffold here. R, C double bond O, O. What's on this side? The phenyl group, right? So it's converting this to an amide, right? This is a little bit different than an actual alcohol, right? Phenol and an alcohol are different from one another, are they not? They have different pKa's. This is a one-step conversion on our chart, right? A one-step conversion. So you'd say no excess. But this is a very special OR group. This is, in essence, like you guys like to say, a trick. This is not a trick, because how do we analyze this? We take the leaving group, and we react it acid-base-wise with the protonated nucleophile, and we get out of that butylamine and phenol. This is 10. This guy is 9. What is this arrow? So what do you think I'm going to do? How much amine am I going to add?
A lot.
Am I going to add 1 mole?
No more.
No. So if I add 1 mole, am I going to get 100% conversion?
No.
No. So really, if you wanted to be a pain in my butt, you'd say 1.5 moles. Or you can absolutely do the math. That's also fine too, and decide you're going to add like 1.67 moles or whatever it is. That'd be fine too. Have at it. Does everyone understand what I mean? Okay. We pause for reflection here. Skipping over H, we go to I. I is also a trick. You guys have the homework out? I. I is also a trick. So what is I like? I is saying that I'm going to take CH3 S minus and react it with the ammonium ion. So what have I started with? Kind of like a thiol, right? It's not exactly a thiol, this here. What does that acid-base chemistry tell me? What's this guy? NH4 plus. 9. CH3SH. 7. What's this guy? Equilibrium. What am I going to do? 2 moles. Excess. Whatever you want to say. Is everyone with me there? Okay. And J is no reaction. Yeah. Isn't that crazy?
What was it?
Damn.
J. Methyl acetate and benzoic acid. You think? Yeah. Is it 10, 7? I think H2S is 7, right? Yeah. That's a big jump. You got Harvard? Don't you think?
I don't have it out.
Water in an alcohol is only like 15.7 and 16. That's interesting. Anyway, that's beside the point. Okay. How do we feel about this? Okay. Does anyone have any other questions about the homework? We are going to start next class with problem 9, and we're going to have more synthesis next class. We're going to start with clickers. Please finish through the workshops so that we can do clickers next class and move on with the materials.